Beryllium is a chemical element with symbol B and atomic number 4. It is created through stellar nucleosynthesis and is a relatively rare element in the universe. It is a divalent element which occurs naturally only in combination with other elements in minerals. Notable gemstones which contain beryllium include beryl and chrysoberyl. As a free element it is a steel gray, strong, lightweight and brittle alkaline earth metal. Beryllium improves many physical properties when added as an alloying element to aluminium, copper, iron and nickel. Tools made of beryllium-copper alloys are strong and hard and do not create sparks when they strike a steel surface. In structural applications, the combination of high flexural rigidity, thermal stability, thermal conductivity and low density make beryllium metal a desirable aerospace material for aircraft components, missiles, spacecraft, and satellites. Because of its low density and atomic mass, beryllium is relatively transparent to X-rays and other forms of ionizing radiation. Therefore, it is the most common window material for X-ray equipment and components of particle physics experiments. The high thermal conductivities of beryllium and beryllium oxide have led to their use in thermal management applications. The commercial use of beryllium requires the use of appropriate dust control equipment and industrial controls at all times because of the toxicity of inhaled beryllium-containing dusts that can cause a chronic life-threatening allergic disease in some people called berylliosis. Characteristics. Physical properties. Beryllium is a steel gray and hard metal that is brittle at room temperature and has a close-packed hexagonal crystal structure. It has exceptional stiffness and a reasonably high melting point. The modulus of elasticity of beryllium is approximately 50% greater than that of steel. The combination of this modulus and a relatively low density results in an unusually fast sound conduction speed in beryllium, about 12.9 km per second at ambient conditions. Other significant properties are high specific heat and thermal conductivity, which make beryllium the metal with the best heat dissipation characteristics per unit weight. In combination with the relatively low coefficient of linear thermal expansion, these characteristics result in a unique stability under conditions of thermal loading. Nuclear properties. Naturally occurring beryllium, save for slight contamination by cosmogenic radioisotopes, is essentially beryllium-9, which has a nuclear spin of 3/2. Beryllium has a large scattering cross-section for high-energy neutrons, about 6 barns for energies above approximately 10 keV. Therefore, it works as a neutron reflector and neutron moderator, effectively slowing the neutrons to the thermal energy range of below 0.03 electronvolts, where the total cross-section is at least an order of magnitude lower. Exact value strongly depends on the purity and size of the crystallites in the material. The single primordial beryllium isotope 9b also undergoes a neutron reaction with neutron energies over about 1.9 MeV to produce 8b, which almost immediately breaks into 2 alpha particles. Thus, for high-energy neutrons, beryllium is a neutron multiplier, releasing more neutrons than it absorbs. This nuclear reaction is 9,4b plus N2 plus 2N neutrons are liberated when beryllium nuclei are struck by energetic alpha particles, producing the nuclear reaction 9,4b plus 4,2he, 12,6c plus N, where 4,2he is an alpha particle and 12,6c is a carbon-12 nucleus. Beryllium also releases neutrons under bombardment by alpha rays. Thus, natural beryllium bombarded either by alphas or gammas from a suitable radioisotope is a key component of most radioisotope-powered nuclear reaction. Neutron sources for the laboratory production of free neutrons. Small amounts of tritium are liberated when 9,4b nuclei absorb low-energy neutrons in the three-step nuclear reaction 9,4b plus N42He plus 6,2He. 6,2He 6,3Li plus beta, 6,3Li plus N42He plus 3,1H. Note that 6,2He has a half-life of only 0.8 seconds, beta is an electron, and 6,3Li has a high neutron absorption cross-section. Tritium is a radioisotope of concern in nuclear reactor waste streams. As a metal, beryllium is transparent to most wavelengths of X-rays and gamma rays, making it useful for the output windows of X-ray tubes and other such apparatus. Isotopes and nucleosynthesis. Both stable and unstable isotopes of beryllium have created in stars, but the radioisotopes do not last long. It is believed that most of the stable beryllium in the universe was originally created in the interstellar medium when cosmic rays induced fission in heavier elements found in interstellar gas and dust. Primordial beryllium contains only one stable isotope, 9b, and therefore beryllium is a monoisotopic element. Radioactive cosmogenic 10b is produced in the atmosphere of the Earth by the cosmic ray spallation of oxygen. 10b accumulates at the soil surface where its relatively long half-life permits a long residence time before decaying to boron-10. Thus 10b and its daughter products are used to examine natural soil erosion, soil formation and the development of lateritic soils, and as a proxy for measurement of the variations in solar activity and the age of ice cores. The production of 10b is inversely proportional to solar activity, because increased solar wind during periods of high solar activity decreases the flux of galactic cosmic rays that reach the Earth. Nuclear explosions also form 10b by the reaction of fast neutrons with 13C in the carbon dioxide in air. This is one of the indicators of past activity at nuclear weapon test sites. The isotope 7b is also cosmogenic, and shows an atmospheric abundance linked to sunspots, much like 10b. 8b has a very short half-life of about 7 times 10⁻17 s that contributes to its significant cosmological role, as elements heavier than beryllium could not have been produced by nuclear fusion in the Big Bang. This is due to the lack of sufficient time during the Big Bang's nucleosynthesis phase to produce carbon by the fusion of 4He nuclei and the very low concentrations of available beryllium-8. The British astronomer Sir Fred Hoyle first showed that the energy levels of 8b and 12c allow carbon production by the so-called triple alpha process in helium-fueled stars where more nucleosynthesis time is available. This process allows carbon to be produced in stars, but not in the Big Bang. Star-created carbon is thus a component in the elements in the gas and dust ejected by AGB stars and supernovae, as well as the creation of all other elements with atomic numbers larger than that of carbon. The innermost electrons of beryllium may contribute to chemical bonding. Therefore, when 7b decays by electron capture, it does so by taking electrons from atomic orbitals that may participate in bonding. This makes its decay rate dependent to a measurable degree upon its electron configuration, a rare occurrence in nuclear decay. The shortest-lived known isotope of beryllium is 13b, which decays through neutron emission. It has a half-life of 2.7 times 10⁻21 s. 6b is also very short-lived with a half-life of 5.0 times 10⁻21 s. The exotic isotopes 11b and 14b are known to exhibit a nuclear halo. This phenomenon can be understood as the nuclei of 11b and 14b have, respectively, 1 and 4 neutrons orbiting substantially outside the classical Fermi waterdrop model of the nucleus. Occurrence: the Sun has a concentration of 0.1 parts per billion of beryllium. Beryllium has a concentration of 2 to 6 parts per million in the Earth's crust. It is most concentrated in the soils, 6 ppm, and is found in 0.2 parts per trillion of seawater. trace amounts of 9B are found in the Earth's atmosphere. In seawater, beryllium is exceedingly rare, comprising only 0.0006 ppb by weight. In stream water, however, beryllium is more abundant with 0.1 ppb by weight. Beryllium is found in over 100 minerals, but most are uncommon to rare. The more common beryllium-containing minerals include bertrandite-2, beryl, chrysoberyl and phenakite. Precious forms of beryl are aquamarine, red beryl and emerald. The green color and gem-quality forms of beryl comes from varying amounts of chromium. The two main ores of beryllium, beryl and bertrandite, are found in Argentina, Brazil, India, Madagascar, Russia and the United States. Total world reserves of beryllium ore are greater than 400,000 tons. Production. The extraction of beryllium from its compounds is a difficult process due to its high affinity for oxygen at elevated temperatures, and its ability to reduce water when its oxide film is removed. The United States, China and Kazakhstan are the only three countries involved in the industrial-scale extraction of beryllium. Beryllium is most commonly extracted from the mineral beryl, which is either sintered using an extraction agent or melted into a soluble mixture. The sintering process involves mixing beryl with sodium fluorosilicate and soda at 770 degrees Celsius to form sodium fluoroberylate, aluminium oxide and silicon dioxide. Beryllium hydroxide is precipitated from a solution of sodium fluoroberylate and sodium hydroxide in water. Extraction of beryllium using the melt method involves grinding beryl into a powder and heating it to 1650 degrees Celsius. The melt is quickly cooled with water and then reheated 250 to 300 degrees Celsius in concentrated sulfuric acid, mostly yielding beryllium sulfate and aluminium sulfate. Aqueous ammonia is then used to remove the aluminium and sulfur, leaving beryllium hydroxide. Beryllium hydroxide created using either the sinter or melt method is then converted into beryllium fluoride or beryllium chloride. To form the fluoride, aqueous ammonium hydrogen fluoride is added to beryllium hydroxide to yield a precipitate of ammonium tetrafluoroberylate, which is heated to 1000 degrees Celsius to form beryllium fluoride. Heating the fluoride to 900 degrees Celsius with magnesium forms finely divided beryllium, and additional heating to 1300 degrees Celsius creates the compact metal. Heating beryllium hydroxide forms the oxide, which becomes beryllium chloride when combined with carbon and chlorine. Electrolysis of molten beryllium chloride is then used to obtain the metal. Chemical properties. See also Category: Beryllium compounds. Beryllium's chemical behavior is largely a result of its small atomic and ionic radii. It thus has very high ionization potentials and strong polarization while bonded to other atoms, which is why all of its compounds are covalent. It is more chemically similar to aluminium than its close neighbors in the periodic table due to having a similar charge-to-radius ratio. An oxide layer forms around beryllium that prevents further reactions with air unless heated above 1000 degrees Celsius. Once ignited, beryllium burns brilliantly, forming a mixture of beryllium oxide and beryllium nitride. Beryllium dissolves readily in non-oxidizing acids, such as hydrogen chloride and diluted H2SO4, but not in nitric acid or water as this forms the oxide. This behavior is similar to that of aluminium metal. Beryllium also dissolves in alkali solutions. The beryllium atom has the electronic configuration He2S2. The two valence electrons give beryllium a +2 oxidation state and thus the ability to form two covalent bonds. The only evidence of lower valence of beryllium is in the solubility of the metal in BeCl2. Due to the octet rule, atoms tend to seek a valence of 8 in order to resemble a noble gas. Beryllium tries to achieve a coordination number of 4 because its two covalent bonds fill half of this octet. A coordination of 4 allows beryllium compounds, such as the fluoride or chloride, to form polymers. This characteristic is employed in analytical techniques using EDTA as a ligand. EDTA preferentially forms octahedral complexes, thus absorbing other cations such as Al3+, which might interfere, for example, in the solvent extraction of a complex formed between B2+ and acetylacetone. Beryllium readily forms complexes with strong donating ligands such as phosphine oxides and arsine oxides. There have been extensive studies of these complexes which show the stability of the OB bond. Solutions of beryllium salts, e.g., beryllium sulfate and beryllium nitrate, are acidic because of hydrolysis of the B4(2+ ion. B4(2+) plus H2O, B3++ H3O plus other products of hydrolysis include the trimeric ion, B336, 3+. Beryllium hydroxide, B2, is insoluble even in acidic solutions with pH less than 6, that is at biological pH. It is amphoteric and dissolves in strongly alkaline solutions. Beryllium forms binary compounds with many non-metals. Anhydrous halides are known for F, Cl, Br and I. BeF2 has a silica-like structure with corner-shared BeF4 tetrahedra. BeCl2 and BeBr2 have chain structures with edge-shared tetrahedra. All beryllium halides have a linear monomeric molecular structure in the gas phase. Beryllium difluoride, BeF2, is different than the other difluorides. In general, beryllium has a tendency to bond covalently, much more so than the other alkaline earths, and its fluoride is partially covalent. BeF2 has many similarities to CO2, a mostly covalently bonded network solid. BeF2 has tetrahedrally coordinated metal and forms gases. When crystalline, beryllium fluoride has the same room temperature crystal structure as quartz and shares many higher temperature structures also. Beryllium difluoride is very soluble in water, unlike the other alkaline earths. However, BeF2 has much lower electrical conductivity when in solution or when molten than would be expected if it were fully ionic. Beryllium oxide, BeO, is a white refractory solid, which has the wurtzite crystal structure and a thermal conductivity as high as in some metals. BeO is amphoteric. Salts of beryllium can be produced by treating B2 with acid. Beryllium sulfide, selenide and telluride known, all having the zinc blender structure. Beryllium nitride, B3N2, is a high melting point compound which is readily hydrolyzed. Beryllium azide, Ben6, is known, and beryllium phosphide, B3P2, has a similar structure to B3N2. A number of beryllium borides are known, such as B5b, B4b, B2b, Beb2, Beb6 and Beb12. Beryllium carbide, B2C, is a refractory brick red compound that reacts with water to give methane. No beryllium silicide has been identified.